Welcome to this video on enzymes. So, what are enzymes? They are large protein molecules that can speed up a chemical reaction, the chemical reactions of life. So these things are biological catalysts. They speed up chemical reactions. Let's have a look at an example. Respiration. The equation you guys should know. Everyone should know this one. It's one of the most important ones you'll ever have to learn. Glucose and oxygen are broken up and reformed into carbon dioxide and water. And enzymes regulate this reaction. They release the energy in controlled stages. If there were no enzymes, this reaction would happen far too slowly for life to exist. In the first part of this diagram, you can see the enzyme colliding with the substrate molecule. The substrate is the reactant. It's the model that's going to be broken down, the starting point. There's a part of an enzyme called the active site. This gap that the substrate molecule fits perfectly into, that's the active site. Here we have an enzyme with the catchy name isocitrate dehydrogenase. By the way, in biology, if you see ASE, A's, on the end of a word, it's probably an enzyme. You can see the active site here shaded in green. So this is where the substrate would dock into this little gap. So the enzyme and the substrate fit together perfectly, and this is called the lock and key mechanism because only your key fits your lock. It's completely specific. The active site changes shape to grip the substrate and strain the bond, and this bond is broken down and the products are released. If you wanted to stop an enzyme working, how would you do it? Okay, if you wanted to theoretically stop an enzyme from working, how would you attack the enzyme? Well, you could change the active site, change the shape of the active site so the enzyme can't join with the substrate anymore. I guess this would be the equivalent of melting your front door key a little bit or taking a hammer to it. You change its shape ever so slightly so it won't fit your lock anymore. You're not getting in your house or your car anymore. Is it possible to do this to an enzyme? Well, yes it is. Extreme temperatures or pH will do this. The enzyme or the active site is said to be denatured. This is the main reason why your core body temperature can't get too far above about 41 degrees Celsius without you dying. So, enzymes are specific. One enzyme only fits one substrate. They're reusable, so they can do this reaction over and over again. They're also extremely fast. One of the fastest is called carbonic anhydrase, and this can do about 1 million reactions per second. It's absolutely incredible, 1 million reactions per second. Enzymes don't just break molecules down. These ones, the ones that break things down, are known as catabolic enzymes. But there are also anabolic enzymes, and these ones build molecules up. Here our food is broken down by catabolic reactions into small soluble molecules that can be absorbed by our intestines, and they can then be built back up again using anabolic reactions into useful substances. Here's a table summarising some of the key catabolic digestive enzymes, and these are the ones that are responsible for the chemical digestion of our food. This graph shows how pH affects the rate of an enzyme-controlled reaction. The optimum pH is the one that works the fastest, the one at which it is the quickest, pH 8. So here, pH 8 is slightly alkali, so this is probably a digestive enzyme in the intestine or something like that. An enzyme in the stomach, like pepsin, would probably have an optimum pH of about 2, because it's pH 2, it's very acidic in your stomach. In this graph, the rate of reaction increases as there are more and more collisions between the enzymes and the substrate. So the initial part of this graph, the upward slope, it's going back to collision theory. If you don't recall collision theory, have a look at the video on rates of reaction. But basically, the more collisions between enzyme and substrate you can get per second, the faster the reaction is going to be. And then it reaches this optimum temperature of about 40 degrees Celsius. This is when that enzyme is at its fastest, and the line starts to curve downwards. The rate of reaction drops after this. And you know why that is. It's because the active site starts to denature and change shape, and then enzyme doesn't work anymore. There we go. That's a very quick, basic run-through of enzymes. Thank you very much for watching.